All right, so let's look at the next one. This is Horner, and we're looking at the APC rotational motion. This is for the multiple choice review. We're going to look at number 31. It says the magnitude of the normal force exerted by the floor on the ladder. So here, this is a ladder. You've got a floor. There is no friction at the top, so no friction at all. But there is friction down here. And so knowing that, there's certain things we really need to think about. One of them is, what is the weight of the ladder? The weight of the ladder is all concentrated right on this point. So this is actually mg right here. And the normal force will then act straight up, and it will be N. And I know that seems unusual since the ladder is at an angle, but that is the way it works with that contact point. Friction is going to be going this way, so as long as that is balanced with the force that we're going to call S up here, then that ladder will not slip, which is kind of cool. We know that if it's just the ladder, the center of mass of the ladder is here, and we're going to call that down to the floor, we'll call that X, and then we'll call the length of the ladder L. And so we've got everything that we need in order to solve both this problem and number 32. So for 31, the magnitude of the normal force, just by looking at the diagram, should be just the weight of the ladder itself. Since there's no friction here, the only thing you have is just a force of the ladder against the wall. So the friction is all concentrated here, and that's keeping that ladder on that wall. The magnitude of the friction force exerted by the ladder on the ladder by the floor is, so what we'll do here is let's think about several things. First of all, we know that the force from the wall on the ladder minus the force of friction should be equal to 0. And that's just saying that the sum of the forces for the ladder should be equal to 0 in the x direction. Let's think about the sum of the forces in the y direction. And we know that that's just the normal force minus mg should be equal to 0. Now we can also think about where the ladder touches the ground, and we can think about that lever arm. So we really here have mg times this position x, okay, so that's the majority of the kind of the torque here, times the cosine of the angle, and we could subtract from that. So this is the torque acting on one end, so if we're trying to keep it from going anywhere, and then the torque on the other end, so that would be the top end, is equal to S times the entire length times the sine of the angle, and that's equal to 0. So we're just making sure that we look at, so for example, if I have the angle here and I do S times L, so S is just that force back, so that's our force. Our position would be L times the sine of the angle. So the length of the ladder is L, so we're just kind of looking at it in these two directions. Sine of the angle would be the opposite side, and then cosine of the angle would be the adjacent side if we do mg. So that's kind of what we're looking at. It's a little bit confusing, but that's kind of the way it works. So from that equation, from these equations, we can say that we know we know that N, I'm going to back up here, N, from this equation, N is equal to mg. So that's pretty easy. And from this equation, we can see F is equal to S. Now, what we'll do here is if we take cosine, okay, minus sine, then we're going to end up with, well, let's just kind of put these together. Here's our S, and that's equal to F. We know mg is equal to N. And so if we say F is equal to S, we can then say that X, okay, that's this position, over L times the tangent of the angle times mg is the force of friction. So that would have to be this direction here. So that would be L times the tangent of the angle, and the tangent of the angle would give the opposite over adjacent, so that's why we've done that. Let's transfer it into kind of what we know. X is going to be 1/2, okay, and L is 1, so this would be 1/2 times mg times, and now 1 over tangent of the angle is actually equal to the cotangent of the angle, and mg is really w, so that'd be w over 2 times the cotangent of the angle. So that should be the answer for this one. Let's go ahead and scroll down and look and see if we have that, and we do. We have w over 2 times the cotangent of the angle. So that's number 31 and number 32. Let's go on and take a look at number 33. So for number 33, we have a 5-meter plank. Has a mass of 100 kilograms, and it rests on top of a building with 2 meters extended over the edge. How far can this 50-kilogram person venture past the edge of the building just before that plank begins to tip? So at this point, it's a uniform plank, 5 meters long. The center of mass is at 2.5 meters. So we know that if this is 5 and this is 2, we have 2.5 meters extending over here. So this is actually 2.5 meters. So we know that we have about half a meter of block that is right here. Half a meter of this board, 0.5 meters, is still on this edge here. For the plank to stay in equilibrium, we know that the sum of the torques has got to be equal to 0, and our angular velocity should also be 0 too. So we could say that mass times gravity times the radius should be equal to the force of the person times their radius. So let's do 100 kilograms times 10 meters per second squared times that 0.5. So that's that little 0.5 part here. And that would be equal to the force of the person, which is 50 kilograms times 10, times their R. If you go through and do this, this actually simplifies and you get 50 is equal to 50R, so our R here is equal to 1 meter, and so our answer is 1 meter. For number 34, it says, which of the following quantities is a scalar that is always positive or 0? And this one's really easy to do. The one that's a scalar that's always positive or 0 is kinetic energy. Remember, it's 1/2 of mass times velocity squared. And so velocity, even if it's negative, our kinetic energy here is still positive. So it is a scalar, and it is always positive or 0. It cannot be negative. Linear momentum and angular momentum could both be negative. Linear if it's going left or in the negative direction. Angular momentum if it's going clockwise. Power and work then, same type of thing. Work could be negative. You can do negative work. And because power is equal to work over time, if you have negative work and don't have negative time, then their power can be negative. For number 35, this question is pretty easy to do. It's kind of strange though. If you're a fisherman or a fisher lady or whatever you want to call it, and you were out fishing, you would not devise this probably to weigh your fish unless you were really desperate. So what they did is they have a tackle box. So we're going to say that this is tackle box T, this is cooler C, and then this is fish F. And what they've done is they're trying to figure out what is the weight or the mass, I guess, of the fish if you can figure out where it will balance. And they found out that it balances at a position of L over 4 from the center of the rope, from the center of the beam that's held up by the rope. If you were to balance just the thing itself, it would balance right in the middle. And so they're trying to do the same thing here to find out using some of the torques what's going on. So here we have a torque that's positive because it will push in the counterclockwise direction, and it's the torque of the tackle box. This would be a positive torque, and it is the torque of the fish. And then the cooler is going to go this way if you would let everything on this side off. So this is negative torque of the cooler itself. And so we better make this that funky looking T here. So let's go through and actually try to solve this one. So if we want to do this for number 35, we've got to say the sum of the torques here should be equal to 0. And so my first torque will be force times the radius. So we're going to get rid of gravity because we know gravity is all the way across. So we're just going to do 3.5 kilograms times L over 2. To this one, we're going to then add the torque of the fish, or the mass of the fish, and so that would be the mass times L over 4. And then from that we're going to subtract the torque due to the cooler, and so we're just going to use mass instead of weight. Since we have G all the way across, we just get rid of it, and that will be times L over 2, and those would all be equal to 0. So at this point we're going to do 3.5 divided by 2, and if you do 3.5 divided by 2, you should get 1.75 times L, plus here we've got the mass of the fish, which we don't know, so that'd be Lm times L over 4, and then we have minus 2.5 times L over just L, sorry, and that's equal to 0. So 1.75 L is what we have on this side, minus 2.5 should give us a value of negative 0.75 L on this side, and that's equal to the negative mass times L over 4. And so if I multiply both sides by 4 over L, so I'm going to do that on both sides, 4 over L, we notice that our L's cross off, and we then can take 4 times 0.75, and we end up with 3, and that's equal to the mass, and therefore our mass is 3 kilograms. And that is number 35, and we're going to stop there.